This video covers Part 1 of Lesson 2-9 for Secondary 1 Math, Writing and Interpreting Exponential Equations. The bacteria population increases by 6 times the previous population per hour. If the sample begins with 5 bacteria, how many bacteria will there be after X hours? So the first thing we want to do is identify the information that we're given. When identifying the information, we look for numbers. So we can see that the bacteria population increases by 6 times the previous population per hour, so 6, and the 5 begins with 5 bacteria. Notice there are no percents here, so we're actually going to use the general form of an exponential equation, which is y equals a times b to the xth power, where a is our initial value and b is our growth or decay factor. Well, in this case, we have y equals our initial value. Well, it begins with 5 bacteria, so it's 5. And our growth factor or decay factor is 6 because it's 6 times the previous population per hour. And we're going to raise that to the xth power. So here's our equation to represent the bacteria population growing. Number 2, fill in the table, then graph. Label the x and y axes. To fill in the table, we're going to substitute in the x values of hours in the table and evaluate so that we find the number of bacteria y. So this looks like taking in the equation y equals 5 times 6 and raising it first to the 0th power, which if we type that into our calculator, we get our initial value, which is 5. To do it for the 0.5 or a half hour, we take y and set it equal to 5 times 6 raised to the 0.5 power. And if we do this, we end up with about 12.2 bacteria. And then we can continue this process. So we'll do 5 times 6 to the 1st power, which would give us 30 bacteria. And then we do 5 times 6 to the 1.5 power, which is about 73.5 bacteria. When we substitute 2 in for x, we get 180 for y. When we substitute in 2.5 for x, we get about 441 bacteria. And when we substitute in 3 for x, we end up with 1,080 for y, so 1,080 bacteria. Now that we have our table filled out, we can graph these ordered pairs in our table. But before we do that, let's label our x and y axes. The x-axis is what is in our first column, and so this would be labeled hours. The y-axis is our second column, and that's going to be the number of bacteria. Now, we can plot our points. So we have 0, 5. So placing 0, 5 on our coordinate plane is going to be really close to 0, 0. Since our scale on the y-axis is by hundreds. Our next one, 0.5 and 12.5, also going to be really close to the x-axis. And then we have 130, so now we're gaining some distance. Then we have 1.5 and 73.5. So we're getting closer to 100. At 2 hours, we have 180. So moving up. And then 2.5, we have 441. So I'm going over to 2.5, going up to 441. And I'm approximating because we're not going to get this exact based on our scale. And our last point, 3, 1,080. So I'm going over 3 on the x-axis, going up to 1,080 on the y-axis. And there's our point. Number 3. How many bacteria will there be after 5 hours? So to solve this, we're going to refer back to the equation we've written for this situation, which is y equals 5 times 6 to the xth power. So to figure this out, we're just going to substitute in 5 for x, because it's after 5 hours. So we get y equals 5 times 6 to the 5th power. And when we type this into our calculator, and round to the nearest bacteria, the nearest whole bacteria, we get 38,880 bacteria. A population of mice triples every month. The nest began with 2 mice. Number 4. Write the equation to show the number of mice after X months. Well, notice we don't have any percentages, so we're going to be writing this in general form, which is y equals a times b to the xth power, where a is our initial value, and that initial value is 2 mice in our situation. And b is our growth or decay factor, and that is the population of mice triples every month. So we're going to substitute these values in, and our equation would be y equals 2 times 3 to the xth power. Now number 5 asks us to fill in the table. And to fill in the table, we're going to substitute in each x value from the table and evaluate for y. So substituting in 0, we would have y is equal to 2 times 3 to the 0th power. And 2 times 3 to the 0th power is just our initial value, which is 2. Now doing it for the next x value in our table, we would get y is equal to 2 times 3 to the 1st power. And 2 times 3 is 6. So we'd have 6 mice after 1 month. Then we substitute in the next one. So y equals 2 times 3 raised to the 1.5 power. And we get 10.39, which doesn't really make sense because we can't have just a part of a mouse. And so we're going to round this to 10 mice. At this point, I would pause the video and fill in the table, and then start the video again and make sure you get the same values in the table. So when you substitute in 2 and you evaluate, you should get 18. Then if we substitute in 2.5 and evaluate, we get about 31.2, but we're going to round to the nearest mouse, so we'd say 31. Then if we substitute in 3 for the number of months, or x, and we evaluate, we would get 54. Okay, a computer was purchased for $1,200 and depreciates in value 25% per year. Number 6. Write the equation to show the price of a computer after X years. So if we look back up at our situation, we know it was purchased for $1,200, so this is going to represent our A, or our initial value. And it says it depreciates in value 25% per year. Since it's depreciating, that means it's decreasing or decaying by 25% per year, which means we're going to use the exponential decay form, which is y equals a times 1 minus r raised to the xth power. And our r is the 25% as a decimal, which is 0.25. So to write our equation, we have y equals $1,200 times 1 minus 0.25, so we could write it as 1 minus 0.25 raised to the xth power, or, as we've been simplifying it earlier, we could write it as y equals 1,200 times 0.75 raised to the xth power. Now my preference is the second one. It's a little simpler and easier to work with when we're putting it in our calculators. Now for number 7, fill in the table, then graph. Label the x and y axes. So we're just going to substitute in again all the x values from our table and evaluate for the y value in dollars. Now each time that we do this, we're going to round our values to the nearest whole dollar. So the first one, when x is 0, that's our initial value. So the value in dollars would be 1,200. Like we did in the previous 2 situations, we're going to substitute in now these x values. So we could get like y equals 1,200 times 0.75 raised to the 1st power, which would give us a dollar value of 900. and then we can continue to fill these in. So go ahead and pause the video and fill them in, and then check. So when we substitute in 2 for x, we get 675 for y. When we substitute in 3 for x, we get about, so I'm going to use these, about symbol, 506. When we substitute in 4 for x, we get about 380. When we substitute in 6, we get about 214. And then when we substitute in 8, we get about 120. And when we substitute in 10 for x, we get about 68. And substituting in 20, we get about 38. Now that we have these values, we're going to graph. So we're going to label the x-axis as years, and we're going to label the y-axis as the value in dollars. Now that we have those axes labeled, we'll plot our points. So 0, and then we have 1,200, which will be right at the top on the y-axis. Then we have 1 and 900. Notice that's in between the vertical lines of our coordinate plane, because on the x-axis we're going by 2's. If we continue to fill in these points, we get 2, and there's 675. And then we have 3 is about 506. And 4 is 380. Next, 6, 214. And then 8, 120. And 10, 68. And 12, 38. And so that's our graph of our situation. Number 8. A pendulum has a beginning height of 45 inches and loses 8% of its height every swing. Write an equation to represent the height of the pendulum after x swings. So notice we have a percentage here. So we have a beginning height, that's A, and then we're given loses 8% in height with every swing. And so this is our percent, or our R as a percentage, which would be 0.08 as a decimal. Since it's losing height, we're actually going to use the exponential decay form to write our equation. So that form is y equals a times 1 minus r to the xth power. So we're going to have y is equal to 45. And then we're going to multiply that by 1 minus 0.08 raised to the xth power. Now remember, we could simplify this, and we could also write this as y equals 45 times 0.92 raised to the xth power. Number 9. What is the height of the pendulum after 15 swings? Round to the nearest hundredth of an inch. So we're going to go ahead and substitute in. Remember how x is our time. In this case, swings is going to be representing our time. And that's because up in the number 8 it said with every swing. So swing is our x value. So we're going to substitute in. We're going to go y is equal to 45 times 1 minus 0.08 raised to the 15th power. And when we type this into our calculators to evaluate it, we get 12.88 inches when we round to the nearest hundredth of an inch. This concludes the Part 1 video of Lesson 2-9 for Secondary 1 Math, Writing and Interpreting Exponential Equations.